Hi there. This is an LSTM cell, or the computation graph of an LSTM cell. It is pretty hideous, as you can see, but what I'm about to show you is even more hideous. This is the computation graph of the LSTM cell augmented with error units, evincing the connectivity scheme of the predictive coding algorithm. So you may see that there are appearing these little red arrows right here that are so-called error units. And these are necessary for an algorithm called predictive coding, which is an algorithm that is a biologically plausible alternative to backprop. And that's what we're going to look at today. Specifically, this paper, as you can see, it is quite a thorough paper. It is called Predictive Coding Approximates Backprop along Arbitrary Computation Graphs. And have you ever heard a more descriptive title of what's in a paper? So the authors are Baron Millage, Alexander Chantz, and Christopher L. Buckley. This paper, as the title says, it looks at this predictive coding algorithm and it shows that this approximates backprop, and we'll see that this approximates is in terms of there is an inner iteration in the predictive coding algorithm, and the more you run that and under certain assumptions, this approximates the backpropagation algorithm. And the new thing in this paper is along arbitrary computation graphs. So there have been papers before describing predictive coding, this algorithm, in various subsettings like fully connected layers and so on. The fact that it approximates backprop there. However, this paper shows that that's actually the case for arbitrary computation graphs. Under certain assumptions, predictive coding approximates the backpropagation algorithm. Why is this important? Because the backpropagation algorithm isn't exactly biologically plausible. So they say right here in the abstract, backpropagation of error, or short backprop, is a powerful algorithm for training machine learning architectures through end-to-end differentiation. Recently has been shown that backprop in multi-layer perceptrons can be approximated using predictive coding, a biologically plausible process theory of cortical computation which relies solely on local and Hebbian updates. So the difference between backpropagation and predictive coding is exactly this point, that predictive coding relies solely on local and Hebbian updates. Okay, and the keyword I think is local. So in a neural network, you have some sort of input X, and you ship it through many layers, layer, and then you have an output Y hat, and then you compare that output using some kind of loss function with your true output that you want, and then there is this backwards phase right here. And in this backwards phase, you want to derive gradients for each of the layers' weights. So each of these layers has a weight associated with it. I'm not going into Greek letters again. So this is W, I don't know, W3, W2 is here, and so on. So what you want to get out is, you want to say, how do I need to change W in order to change my loss for the better? So what you want is this gradient right here. And backpropagation does a very natural decomposition, namely, if you have these hidden states in here, so X is transformed to hidden state H0, H1, H2, H3, so that is the latent representation. If you want, for example, if you want to know how to change weight, or let's say weight 2, the backpropagation algorithm decomposes this into the derivative according to the hidden state at layer 2 multiplied by the derivative of the hidden state by the weight. So this is what you would sort of learn in a beginner's course of deep learning, this decomposition. And of course, in this part right here, this part decomposes into del L for H3, and then H3 by H2. So this is the standard backpropagation algorithm. You can clearly see in the formula, the computation graph, it goes from the L, it flows backward to H3, right? So to H3, and then from H3 it flows to H2, and then from H2 it flows to W2. So that's sort of the flow of the gradient backwards through the network. And that's pretty cool because it allows us to run gradient descent on arbitrary computation graphs, which ultimately enable deep learning, including frameworks like TensorFlow, PyTorch, or the older ones like Theano or LuaTorch, even AutoGrad, things like this. It's pretty cool, but it's not really plausible in the brain because neurons are not bidirectional like this. Neurons generally, I'm not a neuroscientist or anything, but these neurons, they have some sort of soma, and then you have this axon, right? And then this axon goes into many different of these synapses to its children, and it kind of docks onto the somas on the dendrites of the other neurons. And this is not bidirectional. This is generally, here there's unidirectional signal in this direction, and there are so-called feedback connections, so from these neurons to the dendrites of this neuron, but you cannot really send this gradient information. You cannot send this sort of vector gradient information, and you cannot do so in this sort of sweep. So in the brain, it's probably not the case that the layer propagates forward and then sort of waits for a synchronized backward pass across the network in order to update itself. All of this needs to happen much more in parallel, much more local, so that things are only considering local information, not global information, right? Here, for example, you need the global gradient in the update of W2, and you need to have that backpropagated. That's not plausible, so predictive coding comes along. And today we'll look mainly actually at how predictive coding works. Of course, this paper is about extending it to arbitrary computation graphs, which is cool because they do predictive coding for CNNs, RNNs, and even LSTMs. And if you look at let's first jump into the numerical results. If you look at their numerical results, they have lots of these plots where they basically show, we did this network, we train it with backprop, and then we train it with predictive coding, and the lines are just the same. And so it's pretty convincing evidence, even if you go super duper deep. And they do, I think, RNNs with up to 100 layers or 100 time steps unrolled. So the empirical evidence that predictive coding approximates backprop is certainly here. And we'll look at what predictive coding is, how it works, and how it works along arbitrary computation graphs. So that's today's paper, and I hope you enjoy it. If you do, don't hesitate to share it out and subscribe. All right, so this graphic right here compares the two algorithms in principle. On top, very much what I've said so far, the backpropagation algorithm somehow has this signal, it propagates forward, okay, and then at some point there's an output, and if you want to train it, there is a label. You compare that to the output, that will give you an error, and by derivation a gradient, and that gradient is now backpropagated according to the chain rule, according to the backpropagation algorithm. You can see it's very much what I've drawn. The predictive coding algorithm is a little bit different. And it's honestly not super clear from this graphic right here. I find this graphic to be a bit confusing. But you can see, first of all, there is this introduction of these error nodes in the computation graph right here. And there also seems to be the introduction of these new hat, whatever that is. So we're sort of first going to dive into the math and then we're going to check out how the algorithm works as such. So the math right here is a little bit, you have to think a little bit differently than you do in Backprop. So first of all, they say we define a generative model which parameterizes the value of each vertex given the feed-forward prediction of its parents according to this distribution, and a factorized variational posterior, where P denotes the set of parents and C denotes the set of children of a given node X. So this is very special. Namely, this turns the entire algorithm into a sort of a guessing game, into a variational approximation algorithm. So what they're basically saying is that signal, in this type of algorithm, signal isn't just forward propagated, but signal is forward guessed. It's like a bit of a guess. So you have a signal right here, VI, and this is a node in your neural network. And when you forward propagate the signal, maybe this is a fully connected layer right here, so it's simply multiplying it by a parameter, you're not going to obtain the next layer's signal. What you're going to obtain is a guess for the next layer's signal right here. You're only guessing. You're assuming that you're sort of assuming that the true next signal is somewhere in the vicinity of this. So what you do is actually you assume this is a Gaussian with the mean that you predicted, but then there is a good chance it's somewhere around here. So what you do is you'll guess the next layer's signal by forward propagating your own signal, and you're not directly computing it, okay? And the model that we have for that here, why do we do this? We do this because we're also not so sure about this one right here, okay? So this entire thing is built upon, we're pretty sure what the input is, and we're pretty sure what the label is of a data point, but without, we assume we're not really sure what the intermediate layers are, and we're going to run sort of an update procedure on these, on our guesses of where these intermediate signals are. And that's going to be this predictive coding algorithm. So it's called predictive coding, I guess, because you always only predict where the next layer signal might be, and you refine that prediction in a series of inner iteration steps. And that all before you even do a parameter update. So there's going to be an inner iteration to determine what the forward values are of the network. And this is very different from Backprop. There's just a single forward pass, right? Then you know the values, and then there's a backward pass. Here, there is, as you'll see, there is a single forward pass, but then there is an inner loop to refine the forward pass. Before there is a backward pass. And we need this because we only do this sort of local updates. You'll see in a second. So the Gaussian I just drew, so the assumption is going to be that we iteratively refine these guesses of where VI is. And of course, here you'll see that if I change VI to be down here, my next guess, so this is at time step t, my guess is this, my time step t plus 1 is this. Of course, if I apply the same fully connected layer, my new guess is going to be down here somewhere. And so the assumption here that we're going to make is that you can see the value of each vertex is this model right here. This is the generative model, so it's a probability distribution depending on the parents, and we're going to approximate that by this variational posterior, which, as you can see, doesn't depend on the parents anymore. So it basically says that the distribution is not conditional. It sort of stays the same. Not sure if I expressed this quite correctly, but you can see right here they assume a Gaussian for the generative model that's dependent on these things, and then the posterior is simply a factorized Gaussian, and the variational approximation algorithm simply makes the KL divergence between this variational posterior and the true assumed posterior small. And they can prove that this is equal to these errors, and the errors are going to be the errors between what's predicted and what's guessed. Yeah, it's best if I extend this right here, right, I have V0, okay? V0, I'm pretty sure what it is because it's my input. Then what I'm going to do is I'm going to forward guess what V1 is. So this is my guess of V1, okay? Now, from V1, I am going to guess what V2 is. And at the beginning, you know, my guess of V1 is the same as my forward prediction. I have no reason to assume it's anywhere else. So I'm just going to draw this on top of V1 right here. So since, you know, it could be anywhere in the vicinity here, but I'm going to assume it's the same. I have no reason to do so otherwise. And then I'm going to predict V2, okay? And V2, let's say that's already my output layer. And this is my guess of V2. That's already my output layer. But now we're going to compare V2 to our true output, what we desire, our label L, and there's going to be an error, okay? So there's going to be an error right here. And what the predictive coding algorithm does is it basically says, well, look, V2 could be actually anywhere here, anywhere around this thing. It's most likely in the middle, but it could be anywhere. And it's actually quite possible that it's closer to this label than we initially guessed. So it takes this error right here, this red error, and it says, I'm going to update my guess of V2 a little bit closer into that direction. So I don't have it. Here is a new color. So V2 is going to be a little bit closer here. It's possible, right? We simply guessed V2, so it could also be there. It's a little bit less likely. It's a little bit less likely because it's not in the middle of the Gaussian, but V2 could be where L is, right? But now I have to sort of communicate this error back to the last one. And the trick here is that we don't communicate the global gradient, but we only communicate these local error signals. So this first red arrow here is our first error signal, and we're going to communicate that thing back to the previous layer. So the difference between V2 and V, and here is a fully connected, let's say this is a fully connected layer. What we're going to send back to the last layer is this information of, see, you predicted V2 hat, but actually you should predict V2. Please update yourself such that that doesn't, you know, that's a bit closer. So now we're going to update our guess of V1 and say, well, if we moved V1 a little bit over here, that would predict V2 to be up here, right, with the same fully connected layer. And if that's the case, then V2 would be a little closer to the true label. So we're going to move V1 over here. Now we're not going to move it fully because so this is a sort of optimization. There is a force keeping it to where our original guess is, but there is also a force drawing it in the direction of this error signal. You can see. So we're going to say, well, if we just move V1 to up here, we would predict the perfect V2, but also it's less likely. So we're going to find like some sort of a trade-off where it's still quite likely under our Gaussian assumption, but it will predict a little bit more of the correct label, and so on. So this, if we had a longer computation graph, this would then sort of, every node in the computation graph would ask itself, I'm going to guess my own value at a place that is pretty close to my original guess coming from the forward propagation, but also is consistent with the output of the next layer. And the output of the next layer, of course, here is this V2, right? So that the logic isn't, I need to make the loss small. The logic is, well, if the next signal is V2, then I can't be in the middle here. I must be a little bit more up here because, you know, my signal runs through the fully connected layer and outputs V2. So I am probably more up here. So you can see that if you have a computation graph, V0, V1 hat, V2 hat, V3 hat, and so on, if at the end you have a loss signal, you're sort of distributing that loss across this entire chain. So you're kind of building this guessed chain of values, V3, and so on. And that's the output node, which is close to the loss. You're moving all of these things. And now, once you've done this, you can do one step of parameter updates. So once you've guessed all the nodes, well, you can go ahead and say, okay, this is a configuration that is at equilibrium in this sort of algorithm. And now, here is fully connected layer 1. So here is W0, here is W1, W2, and so on, W3. So now we can go ahead and actually update these weights such that the initial guesses that we had and where we truly think the signal is are closer together, okay? So we're now going to update the weights in order to minimize all of these individual errors. And this is also can be done locally. So you see that the parameter update step here is now a local one because we've computed all of these errors between where we initially guess the signal is and where we sort of think it should be. Now we can minimize these errors. So what I've drawn here is actually not exactly the algorithm, but I hope you get the point. So step 1 is you sort of guess where all the stuff is initially. Then at the end, you get an error signal, right? This is an error signal. Then you distribute that error signal backwards. And that is not the same as distributing a gradient. I know it looks the same, but it is not the same. And so I have to say that, you know, they say, oh, this is only local and so on. This doesn't require a backward sweep. I think when I look at this algorithm, it very much does require a backward sweep. So very much it goes from the back to the front. In fact, it goes from the back to the front many times. Now you can do that in parallel. So this node here can update. So to finish the argument here, as I said before, then you kind of wiggle on these nodes to find out, oh, this should probably be more here. This one should probably be more here. This one should probably be more here. This one should probably be more here in order to satisfy, in order to make that error smaller. And the point is that the parameter update step now is a local one, okay? So the parameter update step now only needs these local errors between where you initially guessed and where your refined iterative guess is after distributing the error through the network. And this can all happen in parallel. Okay? All of this updating, sending information around and so on, this can be parallelized, but it does require a backward sweep, if you ask me. Okay, so there are two equations. So there's two things right here. There is first, as we said, there is a phase where the guesses of where our vertex units are, where our hidden representations are refined. And this is given by these dynamics right here. So you see that Vi changes with time according to this thing right here. F is the variational free energy. So this algorithm sort of falls out from the math of assuming these generative models right here under the assumption that they are these Gaussians. Okay. So under this assumption, if you calculate the KL divergence, it turns out to come out to this algorithm right here. So how do we need to update the node Vi? The node Vi is updated according to this gradient, and this gradient is, as we said, only computed as properties of local things. So the first thing is EI, which is so again, if we have, this is our initial guess of Vi, and then here is our refined guess of Vi. EI is the error right here. That's sort of, we need to stay close to our initial guess. But also, we want to go into the direction such that, into this direction right here. So J is the children of Vi. J are the children, and this thing right here says, how do I need to change my guess of Vi to make it fall more in line with Vj? And you see here that's Vj, the initial thing, but then of course the error is, so the error J is going to be the difference between Vj and Vj hat. So ultimately you are guessing, you're saying, how do I need to change Vi in order to make it more commensurate with Vj after going through the layer? Okay, so this derivative right here, this is going to involve the derivative of whatever, the fully connected layer or the conv layer and so on. So there's not no derivatives in this algorithm, but there are only sort of these local derivatives. So EI is going to be the difference here, and then we'll have the fully connected layer using W gives you Vj hat, but also your refined guess gives you Vj, and the error J is going to be this thing right here. Okay, so you want to stay close right here, but also you want to make Vi such that it outputs Vj, such that it also minimizes that error. Okay, sort of. Yeah, it's hard to draw these things, but I hope I've explained it in multiple ways right now, that it's at least a little bit clear how this works. And at the end, once you've reached equilibrium of all of your guesses of where the next nodes are, what you do is you update your parameters here in a local fashion. You can see right here what you need is this error of the ith layer, and you multiply that by this derivative, and this derivative is simply the local derivative of your hidden representation with respect to your layer. Okay, so this is very akin to in the backpropagation algorithm Hi to Wi. This is just this local derivative. So using the update step of the weights now only requires local derivatives, and that's the point. So here it's in this pseudocode, things are a little bit unclear in this, but we'll do. So for the entire data set, X is the data point and L is the label. You fix the start, so you fix V0. Then you do the forward pass. So you do this once. These are your initial guesses. These hat things. You can see the hat things are always computed from the parents. You compute the output error right here. and then begin backwards iteration phase of the descent on the free energy. So here you see there is this inner loop while not converged, and this is just going to work out to be some sort of an inner iterative scheme for a number of steps. This is going to be a hyperparameter, and this is something you can technically do in parallel. You have to send a bit of information around, but you can technically do it in parallel. These inner loops, but you can just imagine it always going from the back, and you distribute these errors. You refine your guesses a little bit, and you start from the back again. You distribute the errors, refine your guesses, and so on. And you do that. You always start from the back in the actual code. So you compute these errors. So this is your initial guess, and this is your refined guess of the current layer. And then you update the vertex values. You say, okay, my guess for the next layer is going to be my guess for this layer plus some sort of this gradient, and this gradient we get from equation number 2, from this thing right here. So my guess is going to be updated such that I still stay close to my original guess, but I also I also predict better what the next layer is. And at the end, when this is converged, you do the update on the weights, and the update on the weights is simply, again, this what we saw. It's the error that you want to correct. So this E is the error you want to correct. Now you have a good approximation of the error once this is converged, times the derivative, of course, with respect to the weights. So the error is in terms of how much are your predictions off from what they should be, and the derivative simply translates that into the how do you need to change the weights such that in the future that error is smaller. Okay. So then they show that this actually approximates backprop, and it's a fairly simple proof. It's sort of a proof by induction, by iteration, that's showing that one such thing like this thing right here at the equilibrium at the last layer is equivalent to backprop, because you can simply substitute this, and then by sort of recursion that goes back the layers. And this is all dependent on you actually reaching that equilibrium, which you do, as we said, by inner iterations. So they have a bit of an example right here where they have this function of it's a pretty simple function, this function right here. The output is the tan of this square root, and there's parameters in there, right? So this is an arbitrary parameter that you might want to learn, and then you give some data sets. So this is equal to 2, but I guess the network doesn't know that. I don't know. So you have to learn it, and they test that. And you can see this augmentation by error graphs makes the computational graph quite a bit more complex. So you have all these error graphs right here, but ultimately it's you could automate this. That is not a problem. Okay, so they also do this for, as I said, CNNs, RNNs, LSTMs, and the results are quite remarkable, I think, in that they just follow the same accuracy and loss and performance patterns of these networks. That's pretty cool. The downside, of course, is that they are way smaller. They're way slower. And they say this sometimes. Due to the need to iterate the V's until convergence, the predictive coding network had roughly a 100 times greater computational cost than the backprop network. Though they say this is a bit misleading because you can distribute and parallelize that. However, as we've seen, it's not fully local. Like you need to send signal around. Every node needs to send signal to its parents or its children. And that, of course, in backprop, you just need to do that once, right? So I'm not exactly buying this argument of this is much more local and so on. So the last thing that I want to point out in the paper, and then we look briefly at the code, is this thing right here. There's a further simplification. They say, importantly, if the edge function linearly combines the activities and the parameters followed by an element-wise nonlinearity, which is most of deep learning layers nowadays, a condition which we call parameter linear, then both the update rule for the vertices and the parameters become Hebbian. Specifically, the update rules for the vertices and the weights become. So here is if you have a linear operation followed by a nonlinearity, which is the fact in RNNs, in CNNs, in fully connected layers, then this here are these update rules. So the local layer derivative is simply going to be your forward activations passed through, and this is a bit weird. It's the forward activations passed through the derivation of the nonlinearity. This is the nonlinearity right here. Times, again, the weights of the forward iteration. And the update rule with respect to the parameters are very, very similar. And the reason I point this out, because now we're going to jump into the code, and I hope you can see this, you can recognize this again. So first of all, let's go into the CNN. Hello. All right, so the code is quite ugly, honestly, but you see that they have backprop CNNs, but they have this thing right here, this this model, which is the one they train, and here is the train function. So in the train function, they go through the data set, and you can see for each data point, they simply call this infer function right here. So this infer function is what ultimately does the training. So in the infer function, they get an input, as you can see, and a label, and a number of inference steps. So they start out by, and this is labeled a bit different. So they have these mu's and the outs, and these prediction errors and the predictions. And we're going to see how that works. So first of all, they go through the layers right here, and I'm going to use my mouse. They go through the layers right here, and you can see they simply forward propagate the signal. So they always take these mu of the last layer, they forward propagate it to get the mu on the layer +1. And the outputs are simply cloned from the mu's. So these must be our news before, or our v's, whatever you want to call them. So one is going to be the initial guess, and the other one is going to be the guess that we iteratively refine, okay? In fact, the mu here is going to be the guess that we iteratively refine. At the beginning, we simply set them to be the same, okay? And then the last layer here, we put at the label, and then the prediction errors, that's going to be, the error variables. So the last prediction error is going to be the derivative of our loss function with respect to the last layer. And now we start this iterative algorithm. So here you see we go through this number of inference steps train, which is going to be like 100 or so. So 100 times we're going to update each of our guesses of the intermediate layers. Then here is what I said. We're going through the layers in reverse order. So 100 times we're going from back to front, back to front, back to front, back to front. And we do that. So here you can see what the first thing we do is we compute the current error, okay, which is the difference between the guess that we currently have and the initial guess that we had during forward propagation. This is going to be 0 for most of the layers at the beginning, except the last layer, right? In the last layer, we've actually put the mu to something else than the output, and thus this error is going to, it's beginning at 0 at each layer as the guesses are the same, but then we're going to refine and refine and refine, and sort of this error of the last layer is going to iteratively propagate through the network to from the back to the front, multiple in an iterative fashion, so multiple times. So once we have the prediction error, we're going to backward this through the layers, and this backward here, that is this this backward edge we saw. Where did we see this? So this backward is going to be this local derivative. In this graph, the backward is going to be the red thing right here. So we take the error of the next layer, and we're going to see how do we need to change the current guess in order to make the next layer's error be a little bit smaller. Okay, so that's going to be the backward function, and we can actually look at the backward function of, let's say, here. So this is the backward function of a fully connected layer. This is the projection layer. There is a fully connected, there's a fully connected layer, and the f is going to be the nonlinearity, and the df is going to be the derivative of the nonlinearity. So in the forward, you can see what we're doing is we're multiplying the input by the weights, and then we're going to save the activations and simply propagate them through the nonlinearity. In the backwards, we're going to take the activations, the forward activation, and we're going to shove them through the derivative of the nonlinearity. And this is why I pointed out, this is this Hebbian learning rule. So first I was a bit confused. Why do we use the forward activations and shove them through the derivative of the nonlinearity? But this is exactly, this is simply because they've derived that this is the correct local gradient, okay? And then we have this, right? This is the local gradient of the layer, and we're going to multiply that by the weights. So this completes the formula that we had right here for these Hebbian updates, this thing. So these are the activations. This is the derivative of the forward layer. We're going to multiply that by the weight again. So this is now the complete derivative, the complete local derivative, which is this thing I've already circled 50 billion times right here. And all we need to do now is we need to multiply this by the error, by the prediction error in that layer. And then we get an idea of how do we need to change this node such that in this one child, and there can be many children, such that in this one child, we make a little bit less error, okay? So that's why we multiply this by E right here. So E is the error, okay? And that would be the backwards thing. So backwards simply tells the parent how it needs to change the child, how it needs to change itself such that the child is a little bit happier. And since this is a forward, a CNN, we don't have multiple children, we simply have one child per parent. So we have a list. And these predictions, as you can see, we simply take the prediction error of layer j+1, we backward it. So how do I need to change this layer in order to make it a little bit more commensurate with the child? And then here is this trade-off. So the trade-off between the prediction error, so how close am I to my original guess? I don't want to go too far away, right? Because I assume my original guess isn't too bad. In fact, there's a Gaussian likelihood model. I want to stay close to that, but also I want to go into the direction such that I make the next layer happier. Okay, so this is this fundamental trade-off. It's computed right here, and it's this minus sign. And then at the end, this is the inference learning rate, and I simply go into that direction of this trade-off. Okay, so I update the guess of the current node like this, and as I said, I go through the network back to front, back to front, back to front, back to front, until I reach some sort of equilibrium. And only when I reach equilibrium, or in this case after this many steps, I then update the weights. And the update the weights function, that's very similar. I think here is update weights. That is simply each layer, I input the prediction error of that layer, and that layer calculates this function right here in much a similar way than you just saw. Maybe we can look at one of them. Let's go. This is layers. Let's go here. Fully connected layer, okay. And you're going to see this Hebbian learning rule again. So activations through the derivative. And so now instead of, so there's a little bit of a difference to before, right? But the difference isn't large, right? So activations multiplied by through this, and then multiplied by the inputs instead of the weights. So that's that. So this multiplied by the inputs instead of the weights, then multiplied by E, which is, so this here multiplied by the error term right here, and that's going to be our local update. Okay, cool. So that's the code. That's predictive coding. And you know, the challenge is, it's not that these people propose this as a true alternative to backprop, but it is a step in a direction of saying, look, the brain with its more Hebbian nature and its more local updates and so on, it could actually be doing something much more close to backprop than we thought, because people thought, well, backprop is impossible in the brain, therefore the brain can't be doing backprop, right? And now we see that actually the brain can do something, possibly, it's not proven, but it's possible that the brain does something that approximates the backprop gradient actually arbitrarily, if all of these, some assumptions are given. But that's sort of the results, and they also show it's quite robust too. Learning rate changes and so on. As we said, we can go pretty deep, even though this is this kind of iterative guessing algorithm under these Gaussian assumptions, under this variational approximation. It is fairly robust and all. So this sort of puts the ball back into maybe the brain is doing something very close to backprop, or at least getting the same results, getting the same parameter updates as backprop. So I hope that wasn't too confusing. I've tried to tackle it from many angles, and maybe after seeing the code, you see it a little bit more clearly. If not, let me know. Open for questions as always. And bye-bye.